We just saw the Metropolis algorithm for MCMC. And next, we need to check that it actually makes sense, that it actually does the right thing for an MCMC algorithm. And so remember that our goal was to approximately sample from this distribution pi, or to approximate this expected value. And our plan for doing that was to construct a Markov chain that had the stationary distribution pi, and then to either, draw samples, run it for a long time and then get a sample at the end, or, take the sample mean as our approximation of this, and that would be justified if we could show that the necessary conditions for the ergodic theorem were to hold. So what we need to do in order for this to be a valid algorithm is we need to check that the Markov chain constructed by this algorithm satisfies the properties that are necessary for the ergodic theorem. So we need to check irreducibility, and that has the stationary distribution pi for this one, and we also need to check aperiodicity for sampling. So let's do that. So first thing we need to do is get our hands on the transition matrix in order to understand this Markov chain. So let's try to figure out what the transition matrix is. So let's think about the value, the entry of the transition matrix that's xi x. So this is just the probability that xi plus 1 equals x, given that xi equals little xi. I didn't have to put I and I plus 1 here. It could be any, this could be any arbitrary k instead of I, but just, to sort of keep things intuitive, let's use I. And what is this probability? So there's two ways for xi plus 1 to take a particular value. First, we sample a value, and then we either accept it, so either xi plus 1 takes that value that we sampled, or we reject, and xi plus 1 is xi. So in order to simplify this a little bit, to simplify our analysis, let's suppose that for the moment that xi plus 1 is not equal to x. So we're going to figure this out in that case. And so this possibility is eliminated. We know that if xi plus 1 is not equal to x, then we're certainly, we couldn't have rejected, because then they would be equal. And so the only way for that to happen is that we got our proposal x and we accepted. So the probability of this is then, it's the probability of sampling x from the proposal distribution, which I'll write using this notation, px given xi, times the probability of accepting x, given that we chose x as a proposal and that we had xi in the previous step. We computed this probability of accepting here, and this is just qxix. So let's write in what this equals. This equals, I'll just put it here. This equals qxix times this thing, min 1 pi tilde of x divided by pi tilde xi. Okay. And if it's equal, so we also need to get an expression if it's equal, so let me put that here. Tx, let's just say txi. What is that? Well, that's just 1 minus the sum of all these others. So we'll just put this. So 1 minus the sum over all x, such that x is not equal to xi of txix. Because it has to be a stochastic matrix. We know T is a stochastic matrix, so it has to satisfy this property. If all but one are determined, that determines the last one. Okay, so that tells us the transition matrix. That's fantastic. And so now we need to figure out if it's, let's first think about if it has the correct stationary distribution. So let's think about that. And the way that we're going to do it is using detailed balance. So I claim, we'll prove this little claim, I claim that this Markov chain that's constructed by the algorithm has the stationary distribution pi, the one that we want it to have. So since we know from the video on detailed balance, we know that if pi satisfies detailed balance with respect to this transition matrix T, then in fact the Markov chain, any Markov chain with this transition matrix, has stationary distribution pi. And so it's enough for us to check that pi satisfies detailed balance with respect to T. So what does that mean? Detailed balance is, of course, just, I'm sort of using this shorthand, pi a for pi of a. I sort of switch back and forth between these two, so hopefully that doesn't confuse you too much. So we need to check that this holds for all pairs of states A and B. Question mark. Does it hold? Well, first, let's think about if A equals B. If A equals B, then it's just pi a TAA equals pi a TAA. So that's trivially true. That's trivial. And then if A is not equal to B, then what? Then let's write out what this left side is. So I'll switch back to this notation since it's going to be hopefully a little clearer. So pi a TAB is pi a. So since I was using this sort of other notation above, I'm switching back. That's, well, we know pi a, and TAB, we just computed what that was, and since a is not equal to b, we're in this case, so it's, what is it? It's QAB times the min of 1 with pi tilde of b divided by pi tilde of a. And now, since pi tilde equals pi up to a normalization constant, so we have this, right? Then if we multiply and divide by z here, then we just get pi of b over pi of a. So in fact, we can rewrite this. We can just do it right here. We'll just replace the pi tilde with a pi. That's equal to that. And now we have pi a over here. So let's multiply that. So we can multiply that into the min, because both of these quantities are non-negative. These are probabilities. These are non-negative, and this is non-negative. So multiplying those doesn't change which one is the min. So we can move that inside the min. So we get pi a times the min of pi a, and pi a times this. The pi a cancels, and we get pi b. Pi b. And now we're in excellent shape, because what did we want to show? We wanted to show that this equals this, right? In other words, if we swapped a and b here, then we get the same thing. And this expression is symmetric in a and b, because clearly the min is, it doesn't matter if you swap these. And by assumption, by our choice of Q, Q is symmetric in A and B. That was part of our choosing. We choose a symmetric matrix. Sorry, symmetric matrix Q, and QAB equals QBA. So therefore, this is true. So detailed balance is satisfied, and therefore xi does indeed have the stationary distribution pi. Proof. Okay, so that takes care of the stationary distribution. And what else did we need? We needed, for the ergodic theorem to hold, well, we also needed irreducibility and possibly aperiodicity if we wanted the second part of the theorem to hold. So I'm going to state another claim, and I won't go through the details of the proof because I think it's plausible enough, and you can take it as an exercise if you want. So assume pi of x is strictly positive for all states x. So under that assumption, if Q is irreducible, by which I mean that a Markov chain with transition matrix Q is irreducible, then a Markov chain with transition matrix T is irreducible. So irreducibility does not depend on the initial distribution of the Markov chain. It only depends on the transition matrix. That's for a time homogeneous, Markov chain. So if you want this xi this Markov chain that we constructed to be irreducible, then it's enough for you to check that the proposal matrix Q that you chose is irreducible. Any Markov chain with transition matrix Q is irreducible. And also, if Q is aperiodic, same thing, a Markov chain with transition matrix Q is aperiodic, then T is also aperiodic. Okay, so I'm not going to prove that, but that's just a simple fact that you can check if you want. And so we have the following result. We have the result of all of our labors that the Metropolis algorithm does what we want. So let's write down what that means. If the probability of x this is kind of a technical condition, if it's strictly positive, and Q is irreducible, then, put then down here, then we have the result of the ergodic theorem, the first part of the ergodic theorem, that the sample mean of f of xi, of the f of xi's, converges with probability 1, or almost surely, to the true mean. And here, of course, x is distributed according to pi in this expression. And further, so that's because if Q is irreducible, then T is irreducible, and assuming this. And we already know by the construction of the Metropolis algorithm that it has a stationary distribution pi. And so those conditions of the ergodic theorem hold. And if further Q is aperiodic, then, put then down here, then the probability that xn equals some value little x, given that x0 equals some value little x0, equals or it doesn't equal, but it converges to pi of x as n goes to infinity. That was the second part of the ergodic theorem, and that holds for any x. So in other words, what this is saying is that if we take our Metropolis algorithm and run it for a long time, that is for a big N, then no matter what state we started it out in, that the distribution of the last the xn, the last state in the chain, this xn here, is going to be approximately, the distribution of that guy is going to be approximately pi of x. So if we want to draw samples from pi of x, then what we can do is just run our chain for a long time and take the ending state as our sample. So under these conditions, that's a valid procedure. And same thing for this, if you want to approximate this. So one thing which is kind of nice about this formulation is that you can use every single x in the Markov chain. We had that sequence of samples, x0, x1, x2, up to xn, and we can actually use all of those, even though they're not independent draws from our distribution. There's a great deal of dependence between successive ones of these. Still, we can just throw them all together into this average, and we have this guarantee that asymptotically it will converge to the right thing with probability 1. So that's a very nice property. And one last thing I should mention here probably is that typically this is not actually what people do. They don't exactly do this, even though this does have this asymptotic guarantee. Let me put as a remark. Typically what people use is instead they use something like this. They start from like m plus 1 and go to m plus n. So they throw out sort of the first m samples, the first m steps in the chain. And they use this to approximate the expected value instead of this full sum. And the reason why is because the first, when you first initialize the chain, you might not, the distribution of the first xi's, of x1, x2 up to xm or so, the distribution of those might not resemble this pi distribution very closely at all. And so you don't really want to include those in this approximation because they're not really good samples. So that first that sort of initial set of samples, for some, you choose this for some sufficiently large m, and that what sufficiently large means all depends on your problem, and can be very difficult to figure out what m should be. But this m, so this 1 through m, or maybe 0 through m, is called the burn-in period. So if you hear that phrase, or the burn-in phase, if you hear this term, that's what it means. It's you sort of need some time for it to really sort of be a good approximation to the true distribution that you're trying to get, pi.